everyone. Today we will going to see some practice questions from the chapter General Organic Chemistry. This is part 2. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Moving on to index, we will going to see the practice questions from question number 8 to question number 40. So let's start with the question number 8. In which of the following functional group isomerism is not possible? So we have to tell that we have given some functional groups in the options. We have to tell that in which of the options the functional group isomerism is not possible. So options are alcohols, aldehydes, alkyl halides, or cyanides. You have 10 seconds to solve this question. After that, we will see the answer. Let's see. So the correct answer is option C, that is alkyl halides. So alkyl halides do not show functional group isomerism. This is a concept which we use to answer this question, and thus alkyl halides is the correct answer. Alkyl halides are basically halides is for halogen, right? Halogen group is group 17. Fluorine, bromine, chlorine, iodine, okay, all these elements are halogens. So when they are combining to the alkane group like methyl bromine or methyl iodide, okay, that is known as alkyl halides. So alkyl halides are the groups which do not show functional group isomerism, and thus the C option is the correct answer. Okay, let's move on to the next question. Question number 9. Identify the compound that exhibits tautomerism. Tautomerism is a concept, and in the question it is asked that we have to identify the compound given in the options which exhibit tautomerism. Options are 2-butene, lactic acid, 2-pentanone, or ethane. You have 10 seconds to solve this question. After that, we will see the answer. Let's see. The correct answer is option C, that is 2-pentanone. So tautomerism is due to the spontaneous interconversion of two isomeric forms with different functional groups into each other. So basically, tautomerism is a concept which is observed due to the interconversion, or you can say spontaneous interconversion of the two isomeric forms. We have two forms like this, you can see. We have two forms which is spontaneously interconverting into each other, and they both have different functional groups with them. The term tautomer means constitutional isomers that undergo such rapid interconversion so that they cannot be independently isolated. That means if you want to, stabilize or get the individual compound, you cannot. The process of interconversion is that fast. So they are always, in a rapid interconversion process. So they cannot be independently isolated. That is the means of tautomer. And tautomerization is the concept in which this is happening, this process is happening. You can see this is the keto form in which ketone C double bond O is present. And it is interconverting like oxygen. This double bond will go on to the oxygen as a lone pair. And this hydrogen bonds will come here as a double bond, and the hydrogen which is reattaching from carbon gets attached to the oxygen, because oxygen donates its lone pairs to the hydrogen and form a bond here with the carbon of OH. So you can see it will form enol C double bond CH here and C single bond OH here. So this is interconversion. It will be converting to this, then this will be converting to this. So this is a process. So this process is tautomerization. This concept is tautomerization. So basically it is shown by the ketones, right? That's why in the question we have asked that identify the compound that exhibits tautomerism, that show tautomerism. So only the one option is from ketone group, so that is 2-pentanone. Thus C, that is 2-pentanone, exhibits tautomerism, and thus our C option is the correct answer. Okay, let's move on to the next question. Question number 10. The number of stereoisomers possible for a compound of the molecular formula CH3, CH, double bond, CH, single bond, CH, OH, and this OH is basically connected to this carbon, and this Me is also connected to this carbon. Okay. We have given this compound. We have to tell the number of stereoisomers possible for this compound. Options are 3, 2, 4, or 6. You have 10 seconds to solve this question. After that, we will see the answer. See? So basically, the correct answer is option C, that is 4. So 4 is the number of stereoisomers which is possible for the given molecular formula compound. So for the given compound, the total number of stereoisomers are 4. There are 2 stereogenic center in the given compound, and the number of stereoisomers thus we count as 2 to the power n. N where is the sum of the geometrical isomers possible plus the chiral carbon present. Okay, so n is the sum of, so n will be equal to 2 because there are 2 stereogenic center. One is this carbon, which is chiral carbon, having all the attached, attached groups are different. Like carbon is attaching to one hydrogen, one OH group, one methyl group, and one side is this whole chain, right? So this will become a chiral carbon, and you can see that a double bond is also present between two carbon atoms, due to which we can get 2 form of cis or trans form of isomers for this. So n will become 2 because n is the number of the isomers possible plus the chiral center. So n will become 2. So 2 to the power 2 will be 4. And thus the total number of stereoisomers possible for the given compound will be 4. And thus our C option is the correct answer. Now let's move to the next question. Question number 11. 3-methyl pent-2-ene on reaction with HBr in presence of peroxide forms an addition product. The number of possible stereoisomers for the product is. Options are 6, 0, 2, 4. You have 10 seconds to solve this question. After that, we will see the answer. Okay. Let's see. So the correct answer is option D, that is 4. So the number of stereoisomers in the molecules which are not divisible into 2 equal halves and have n number of asymmetric carbon atom will be equal to 2 to the power n. Okay, so if you want to find out the number of stereoisomers, it will be equal to 2 to the power n. And 3-methyl pent-2-ene. This is the structure of 3-methyl pent-2-ene if you want to see. So at the third position, we have the methyl bond here, right? Like here, one methyl group is attached to the third carbon. And at the second carbon position, a double bond is present between the second carbon and the third carbon. So that's why. And in the main chain, in the parent chain, we have 5 number of total carbon. So you can see that it is 2-methyl-pent-2-ene, 3-methyl-pent-2-ene. So 3-methyl-pent-2-ene on reaction with HBr in the presence of peroxide forms an addition product. That means addition reaction is happening between HBr and 3-methyl-pent-2-ene, and we will get 2-bromo-3-methylpentane as a product. It has 2 chiral centers, and therefore the 4 stereoisomers are possible. So you can see that on reacting this initial compound given with the HBr in presence of peroxide, we got our final product as 2-bromo. At the second position, bromine is attached, so 2-bromo. At the third position, a methyl group is attached to 3-methyl. Pentane, because no double bond is present, so alkane, and there are 5 number of carbon atoms in the parent chain, so pentane. So it will be 2-bromo-3-methyl-pentane. Anti-Markovnikov's addition is happening here. 4 stereoisomers are possible as molecule is having 2 chiral centers and is asymmetric. One is at third position because one hydrogen, one this group, and one methyl is present. And at the second position, one bromine, one hydrogen, one methyl group, and one this whole group. There are 2 chiral centers are possible. So 2 to the power 2 will become 4. So that's why 4 number of total stereoisomers is possible for the 3-methyl-pent-2-ene on reaction with HBr, and we get this product. So on this product is having 4 number of stereoisomers, right? And thus our option B is the correct answer. Okay, let's move on to the next question. Question number 12. Which of the following compound will exhibit geometrical isomerism? So in the following compound in the options, we have asked which one exhibit the geometrical isomerism. Options are 1-phenyl-2-butene, 3-phenyl-1-butene, 2-phenyl-1-butene, or 1,1-diphenyl-1-propene. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. So the correct answer is option A, that is 1-phenyl-2-butene. So we have asked that which compound show the geometrical isomerism. So alkene, in which different groups are attached with the double bonded carbon atoms, exhibit the geometrical isomerism. So you can see here that in the case of 1-phenyl-2-butene, carbon double bond is present here and here between these 2 carbons, right? And different groups are also attached to these 2 carbons. So we can write it in the 2 geometrical isomers form. First one is trans 1-phenyl-2-butene, in which you can see that hydrogen is attached to the opposite to each other. And second one is cis 1-phenyl-2-butene, in which hydrogen is attached adjacent to each other. So it is cis, right? So there are 2 geometrical isomerism which we can draw for the 1-phenyl-2-butene, because there is a 1 double bond present between the carbon, and those carbon is having different groups, side chains attached to it. So it will show the geometrical isomerism. Okay, and in 3-phenyl-1-butene, same group does not show geometrical isomerism, because you can see that there is this double bond between the carbon. There is a hydrogen, and there is one side hydrogen, and there is this phenol chain. So in the 3-phenyl-1-butene, same group does not show geometrical isomerism, because the double bond between 2 carbons is present, but on these carbons, different atoms is not present, right? In 2-phenyl-1-butene, same group does not show geometrical isomerism. Again, in this case also, the same group does not show the geometrical isomerism. 1,1-diaphenyl-1-propane being an alkane, saturated compound does not show geometrical isomerism. And in the 1,1-diaphenyl-1-propane, being an alkane, because it is an alkane, right? As the name says, propane is written here. So as the name says, alkane, so it is a saturated compound. So saturated compound does not show geometrical isomerism, and that is why the 1,1-diphenyl 1-propane also does not show any kind of geometrical isomerism. 2-phenyl 1-butene will also not show the geometrical isomerism. 3-phenyl 1-butene also not show the geometrical isomerism, and only this 1-phenyl 2-butene will show the symmetrical isomerism as a cis and transform, and thus our A option is the correct answer. Okay. Now let's move on to the next question. Question number 30. Which of the following compounds will show metamerism? It is also a process of isomerism, metamerism. We have to tell that which compound from the options show the metamerism process. Options are CH3COO C2H5, C2H5S C2H5, CH3O CH3, or CH3O C2H5. So you have 10 seconds to solve this question. After that, we will see the answer. The correct answer is option B, that is C2H5, sulfur C2H5. So metamerism is possible in ethers, thioethers, secondary amines, esters, etc. The metamers belong to the same family but differ in the nature of alkyl groups. So alkyl group can be different. For example, C2H5S, C2H5 will show metamerism. Okay. So as it belongs to thioethers, that's why this will be the answer, that it will show, this is the compound that will show the metamerism property, and thus B option is the correct answer. Okay, now let's move on to the next question. Question number 40. Nitroethane can exhibit one of the following kind of isomer. So we have given different kind of isomerisms in the options. We have to select one isomerism which is shown by the nitroethane compound. Options are metamerism, optical activity, tautomerism, or position isomerism. You have 10 seconds to solve this question. After that, we will see the answer. Let's see. So the correct answer is C option, that is tautomerism. So nitroethane exhibits tautomerism. You can see that this is the nitroethane. Ethane group, that means CH3CH2, ethyl, and NO2 is attached to the ethyl group, nitroethane. And it is going to the tautomerism process and forming the double bond between nitrogen and carbon, and the OH and the nitrogen single bond, right? This is the process of tautomerism, right? That double bond between the oxygen is converting to the OH single bond. So tautomerism is the kind of isomerism which is exhibiting by the nitroethane compound given in the question, and thus the C option is the correct answer, that is tautomerism. Okay, thank you.